Alright, thanks for watching, and today I will evaluate the integral of square root of x squared plus 1. And it's really cool because you'll see it involves some very neat calculus techniques, including integration by parts and trig substitutions. And in fact, in a previous video, I did the square root of 1 minus x squared, and for that we needed a specific trig substitution. And here we need another one. Namely, the first step is to notice, well, we somehow want to simplify this square root. So we're looking for something of the following form. So this really looks like something squared plus 1 equals to something else squared. And there's one trig identity that's very suitable for this, namely tangent squared plus 1 equals to secant squared, which suggests that we should use the substitution x equals to tangent of theta. So let's do that. X equals to tangent of theta. Okay? And just one little technicality that will be very useful later on. If we have x equals to tangent of theta, we want tangent to be 1 to 1. So it might be useful to choose theta to be between minus pi over 2 and pi over 2. That's one thing. And then if x equals to tangent of theta, dx is secant squared theta d theta. And the square root business here, square root of x squared plus 1 is square root of tangent squared plus 1, which is square root of secant squared, which is absolute value of secant of theta. And in fact, here is where the fact that theta is between minus pi over 2 and pi over 2 comes in handy, because suppose your angle is between minus pi over 2 and pi over 2. So in other words, this region here, notice that secant of theta, which is 1 over cosine of theta, is in fact positive here. Which means, in fact, if you made the mistake of removing the absolute values, here you're lucky, because here it does work. So this function is positive, so you can legitimately say that this is secant of theta. And therefore, our integral now, integral of x squared plus 1 dx becomes integral of secant of theta, and then dx becomes secant squared of theta d theta, and that becomes integral of secant cubed theta d theta. In other words, great, using a trig substitution, we remove the square root, but then we're left with this very ugly integral. And now let's calculate that very ugly integral. I mean, in math we don't really judge, every integral is alike. But here, the point is we still have a nasty integral, whatever. Okay. So step 2 is to evaluate that integral, and let me call this I. And you'll see why in a second. So I equals to integral of secant cubed theta d theta, but this is hard to manage. And in fact, let's simplify this a little bit. So if you like, this becomes secant squared theta times secant of theta d theta. Okay, why did I do this? Because notice, this part is easy to integrate. This part is easy to differentiate. So when you have this balance between integration and differentiation, this really calls for integration by parts. So, integration by parts, don't break my heart. So du is secant squared theta, v is secant of theta, u becomes the tangent of theta, and dv is secant theta tangent theta. So we get that I equals to, so uv tangent theta secant theta minus u dv, so tangent secant tangent, so it's equal to integral of tangent squared theta secant theta d theta. But it turns out we can simplify this because, again, using our trig identities, we have tangent squared is secant squared minus 1. So this becomes tangent theta secant theta minus secant squared times secant is secant cubed theta. And then plus the integral of secant theta d theta. So what do we have? I equals to tangent theta secant theta. Oh, what do we have here? This is the same as I. Remember, I was the integral of secant cubed. So minus I. And then this you can evaluate. So that's ln of secant theta plus tangent theta plus a constant. Which means, in fact, here you have an equation for I, which you can solve. So we can literally solve for our unknown integral. So we have 2I equals to tangent theta secant theta plus ln of secant theta plus tangent theta plus c. Which means that I equals to all this divided by 2. So step 3, we in fact have I equals to 1/2 tangent theta secant theta plus 1/2 ln of absolute value of secant theta plus tangent theta plus. So a constant divided by 2, but the constant is just a generic constant. So in fact, we can just replace c over 2 by c. So let's just write c. And that's good because we solve for our integral. The only problem is, remember it was the integral of square root of x squared plus 1. Ideally, in the end, we want to have something in terms of x. Well, which means we have to solve for tangent theta and secant theta in terms of x. But recall, what is x? X equals to tangent of theta. Right? Which means that tangent of theta equals to x. So that's the first thing. We can replace tangent by x. What about secant? For this, we have to use the triangle method. What does the triangle method say? It says, find the easiest triangle with the property that tangent of theta equals to x. So here, let's say we have a right triangle. This is an angle theta. And tangent, remember, is opposite over adjacent. So in order to have tangent of theta equals to x, let adjacent be x, and opposite be x and adjacent be 1. Then that works. And then what is secant? Secant is hypotenuse over adjacent. Theta equals to this over 1. Okay. But what is question mark? Well, by the Pythagorean theorem, that's just square root of x squared plus 1. Which is great, because we have all our ingredients to write what I is. So I then just becomes 1/2 x times square root of 1 plus x squared, I guess x squared plus 1, plus 1/2 ln of square root of x squared plus 1 plus x plus a constant. Don't quote be honest, I believe you can also remove the absolute value, but it's too risky for now. Alright, thank you so much. If you like that integral and other fun integrals and more general math topics, please make sure to subscribe to my channel. Thank you.